End-to-end neural image compression achieves state-of-the-art rate distortion performance in research papers, yet you will almost never encounter it in a production environment. The models are simply rejected by the real world. The reason is an insurmountable infrastructure wall. Billions of edge devices, smartphones, and web streaming servers are hard-coded with dedicated silicon to decode standard JPEG and MPEG bitstreams. The machine learning community operates on the assumption that deep learning will eventually replace these classical codecs entirely, proposing formats that require entirely new decoders. This benchmark comparison table highlights the fatal deployment flaw of end-to-end neural codecs. Despite their high theoretical performance, they offer 0% backward compatibility with existing hardware. Standard JPEG decoders offer 100%. Max Ehrlich's 2022 dissertation proposes a different approach. Rather than fighting legacy decoders, we can embed the mathematical first principles of JPEG and MPEG directly into the architecture of deep neural networks. By integrating codec logic, this architecture achieves up to a 43.6% reduction in bitrate, recovers lost computer vision accuracy under severe compression, and maintains total backward compatibility with legacy hardware. True innovation in digital infrastructure does not require replacing the internet's legacy pipes. It requires engineering deep learning to flow natively through them. Standard machine learning pipelines waste massive amounts of compute by fully decompressing JPEG bitstreams back into raw spatial RGB pixels before processing them. This animated grid demonstrates an alternative interception point. The incoming image is split into 8 by 8 blocks, and a 2D orthonormal discrete cosine transform, shown by this mathematical equation, converts those spatial blocks directly into frequency data. Frequency component rearrangement, or FCR, bypasses spatial decompression entirely by extracting the 64 frequency coefficients from each block and stacking them along a new z-axis channel dimension. The resulting structure is a unified 3D tensor. Channel 0 holds the DC luminance, while channels 1 through 63 capture progressively higher spatial alternating current frequency modes. Neural networks can operate natively in this space because both the 2D DCT transformation and spatial convolutions are exact linear operators over vector spaces. This linearity allows spatial 2D convolutions to translate directly into DCT-domain tensor contractions, computable with a single PyTorch einsum command. By operating in the transformed frequency domain, the neural network processes feature maps at 1/8 the spatial resolution, drastically reducing the memory bandwidth required for high-resolution images. FCR flips classical compression from a processing bottleneck into a massive computational shortcut for neural networks. Working in the JPEG domain introduces the multi-quality problem. Compression artifacts do not have a uniform signature. Their severity depends entirely on the specific quality factor applied during encoding. Historically, correcting these artifacts required training, storing, and deploying a completely separate neural network for every specific quality level, rendering production deployment highly impractical. This diagram illustrates a dynamic hypernetwork called Convolutional Filter Manifolds. It extracts the compression metadata, morphing the original quantization table into a single 1D vector of inverse quantization step sizes. That inverse vector flows directly into an auxiliary multi-layer perceptron. The MLP digests the metadata and dynamically generates the network's 4D convolutional filter weights on the fly. The quantization-guided artifact correction engine, or QGAC, applies these freshly generated weights to smoothly process the incoming DCT feature maps. By treating convolutional weights as a dynamic manifold conditioned on codec metadata, a single deployed architecture adaptively restores images entirely blind to their initial compression level. Human eyes prefer image restoration that smooths out high-frequency noise. Machine vision models, however, require sharp edge gradients to identify features. When you apply standard perceptual restoration logic, like mean-squared error, to a heavily quantized image, it actively harms computer vision pipelines. Critical topographical edge cues dissolve into a smooth, featureless gradient that neural backbones cannot parse. This block diagram details the task-targeted fine-tuning pipeline, which places the QGAC restoration module directly upstream of a frozen ResNet backbone model. Standard pixel loss is discarded entirely. Instead, the network computes downstream classification and bounding box losses, propagating those errors backward to tune the QGAC weights. The enterprise deployment advantage is significant. The heavy, computationally expensive vision backbone remains completely frozen. Only the lightweight QGAC module updates. On benchmarks like ImageNet and COCO, this targeted fine-tuning recovers up to 92% of the backbone accuracy that was originally destroyed by severe compression. Prioritizing mathematical edge gradients over perceptual human smoothness scales enterprise machine vision effectively on highly compressed data. The architecture extends beyond static JPEGs to address the temporal complexity of MPEG and H.264 video streams. Standard video machine learning models discard the metadata embedded inside these codecs, wasting compute by forcefully recalculating optical flow from raw, uncompressed pixels. The Metabit engine bypasses this redundant step. As shown here, it extracts raw motion vectors directly from the encoded bitstream, using them to warp and align a past reference frame onto the current target frame. After alignment, the network must restore the frames. That standard pixel loss introduces two severe risks to video: temporal flickering between frames and the over-smoothing of vital textures. This formula introduces the multi-scale difference of Gaussians, or DOG, loss to supervise the restoration. Notice the summation across specific octave scales: 1, 2, 4, and 8. This specific loss function acts as a bandpass filter, isolating the spatial frequency octaves most severely degraded by lossy video codecs. By evaluating multi-scale structural differences rather than pixel-level targets, the network is forced to restore high-frequency textures without hallucinating false artifacts. Metabit aligns bitstream temporal metadata with spatial frequency supervision to output temporally consistent video, completely eliminating the need for redundant optical flow estimation. The fully assembled architecture, combining QGAC and Metabit, demonstrates strong empirical outperformance across major datasets. This table summarizes results against state-of-the-art JPEG restoration. It achieves a 0.85 decibel PSNR gain, yields a 43.6% storage reduction, saving 29.5 kilobytes per image at equivalent quality for real-time edge processing, and maintains 100% compatibility with legacy web browsers and media hardware. The system does have strict technical limitations. QGAC fails to restore images that have undergone multiple recompressions or images saved pristine at a quality factor of 100, because the inverse quantization vector provides no discriminative signal. The architecture relies entirely on metadata. The system crashes if prior transcoding steps have stripped the J5 quantization headers from the files. Finally, while spatial dimensions are smaller, the dynamic weight generation via CFM hypernetworks strictly requires GPU acceleration, making it computationally heavier than standard CPU C-based decoders. The future of applied machine learning does not always require tearing out the existing infrastructure of the internet. By weaving deep neural networks into the classical first principles of the codecs we already rely on, we scale advanced vision tasks directly on the systems that power the world.